begin our talk. Björn, the stage is yours.
All right. Let me share the screen. Most famous Zoom words everyone has heard in the past years. All right, so you should see my slides now. Okay, so personally I thought there's like an introduction slides, first of all, which is being done by Janef or Lukasz, but I can quickly introduce myself as well. My name is Björn. I'm a senior software engineer at Newstore. I'm joining you remotely because I'm sitting on the other side of the pond. So I'm sitting in Boston. It's the first time I'm presenting at the Berlin Go meetup. I have presented at the Boston Go as well before, but it's the first remote talk across the pond, so to say. And today's talk is about TinyGo, and the catchline here is basically going small on microcontroller and WebAssembly. And just to outline a little bit what I have prepared for you today is I first want to talk to you about what is TinyGo, how small is TinyGo. Then also there's a difference between small and tiny. So the first thing is how small. The second one, or the third point in the agenda is how tiny is it? How did the TinyGo creators achieve that? How would you get started with it? And then I have prepared some examples. I have 3 examples for WebAssembly and 6 examples for Arduino Nano prepared for you. And I will share the GitHub repository link at the end of the presentation with you. So if you're not able to read all the code, and I will not go over all code in detail, you can read it up online afterwards and follow at your own pace again. I will also see that I can make the slides available afterwards publicly. Okay, so what is TinyGo? If we look at the definition on the website from TinyGo, it's a compiler for small places. It is open source. The code is available on GitHub. When I created these slides, it had over 12,000 stars. It had around 700 forks available, and around like 130 to 140 contributors have contributed code to TinyGo. Also, most of the Go language is supported. And here's a small list of what is supported. It's just like a excerpt of what I think is interesting to see. Of course, there are more things supported. So first of all basic types and control flows, including switch statements, are supported. Go routines and generics. And yes, you heard it right. You can run Go routines and generics on a microcontroller. Personally, for me, I find that very amazing because I don't know if anyone of you ever tried to do something with microcontrollers and tried to do something with threading or some kind of like Go, what Go is doing with coroutines. It's not a pleasant experience. So I feel like having Go routines on a microcontroller is like an awesome feature. And also that you can run generics is, for me, it's mind blowing. You can have defer, you can have slices. In most of the cases, interfaces will work. We have Go modules available, and you can even also embed files in your own, in the final binary. So if you need some additional assets or whatever you want to do with your microcontroller, if you need that, you can even embed that into your binary. The link down here shows you like the full list of what of the Go language is supported. You will see that in some places they marked, okay, it will run. And then they also have a separate column of how much of the tests will work, because there's a difference between the library is working and the tests are working. So if we talk about small, 1 second. So if we talk about small, so since TinyGo is a compiler for small places, so how small is small then? So you can start off with, you can run TinyGo on a Switch. That is still a fairly big device, so it's not really small. You can even run it on a Game Boy Advance, still fairly big. Say let's step like 1 step smaller, and you can even run TinyGo on like a plenty of Arduino boards. So here in this example, you see Arduino Uno board, but you can run it on an Arduino Nano 33 IoT, and you can even run it on Arduino boards which have not only ARM-based chips, but you can also run it on a Raspberry Pi power chip. So there is like a Arduino Nano RP2040 available, which you can also program with TinyGo. But still, I consider that still very big. So we can even go 1 step further down, and you can run TinyGo on microcontrollers as small as ESP8266 or ESP32. And just to give you a reference for how big a ESP microcontroller is, it's about the diameter of a $0.25. And in European measurements, it would be around like 24 millimeters. So it's like 0.75 inch or something like that. So this is how small you can go on TinyGo, and still being able to run Go on such a small device, it's incredible. But apart from microcontrollers, you can also run WebAssembly. And just to give you an overview of what WebAssembly is, it's a new type of code that is runnable in modern browsers. It has an assembly-like structure. You can have near real-time or near native performance. So it's almost comparable as if you would run a regular Go binary in your on your computer instead of running something compiled for WebAssembly. It has compilation targets for different languages. So you can run C#, you can run like the regular Go with it, you can run TinyGo. So you can have like a long list of programs of programming languages that are available for TinyGo, for WebAssembly. And also one interesting and important feature is it can run alongside JavaScript, allowing that both the WebAssembly application as well as JavaScript can interact with each other, as I will show you in an example later. Overall, TinyGo supports around 86 microcontrollers as of creation of the presentation, and the number of these microcontrollers keeps constantly increasing. When I started first with TinyGo, like 2-3 years ago, it was like around, I would say 60 or 65 microcontrollers. Now it's up to 86 microcontrollers. There are drivers available for TinyGo. So you can have around 90 different sensors and displays are supported, what you can connect to your microcontroller and run. So you can run e-ink displays. You can run DHT, temperature and humidity sensors. TinyGo has drivers for Wi-Fi. It has drivers for multicolor LEDs. It has SD card drivers so that you even can persist files from your application on a microcontroller. Also, this number of drivers is constantly growing. So if you look maybe in like 2 months from now, it might be over 100 supported drivers here. It has TinyGo offers plugins for Visual Studio Code and Golang. And the Visual Studio Code plugin even offers you a preview so that you can run your program without having to flash it to the microcontroller first. And also the preview is available at play.tinygo.org. So you have like a playground similar to the Go playground, but here you actually have a output. You actually see a microcontroller and you can interact with LEDs and buttons. And I will show you the playground in an example later. As I said in the beginning, there is a difference between small and tiny. So the small part was the size of the microcontrollers. now I want to highlight a little bit about how tiny it is. So if we just look at a standard Hello World application, which does nothing else than importing the FMT package and then just printing out Hello World. Here in this picture, you see how you would compile such binary. So you just show, okay, you say go, in this example, I just want to compare both like the regular Go binaries and the TinyGo binaries. So I just built like the binaries with the regular toolchain and the TinyGo toolchain. So both commands are very similar. But if we now take a look at the output here, if we now do a ls-al afterwards, you see that the regular Go application is a whopping 1.8 megabytes. And for a microcontroller, which maybe has like 256 kilobytes of flash memory, this is like way too much. If we now look at the TinyGo application, you see that this is only 33 kilobytes. And that, on the other hand, fits very easy on a microcontroller. Also, the output is similar if you compile a WebAssembly application. The regular Go application here is 2 megabytes, and the TinyGo is 179 kilobytes. And if you now want to develop a WebAssembly application and you want to run this on a mobile device, downloading 2 megabytes of data, maybe via a spotty internet connection, versus 179 kilobytes is a difference. So it makes loading the application significantly faster. And how is all of that achieved? Well, I would say it's as with every other new compilers and new programming language. Someone was bored and thought, okay, let's do something with LLVM. And that's what the creator of TinyGo did. So they just took LLVM and created a new compiler based on that structure. And on this slide, you'll see a rough overview of the pipeline. So when you type TinyGo build, these are roughly the steps which are executed from the TinyGo toolchain to compile your binary and even upload it. More details of that can be found on the link, which is shown below. But to give you a rough understanding is that we first use the regular Go toolchain to do the lexing and parsing step. And afterwards, the toolchain is generating something called single static assignment. And that's still using the Go SSA toolchain. Afterwards, the TinyGo compiler interprets that output from the Go SSA step and then runs some optimizations afterwards on it. And then it passes this to LLVM to generate something which is called intermediate representation, which is then analyzed by LLVM. And then eventually you have the main hex file, which is then generated and uploaded to the machine. So how would you get started with TinyGo? So first of all, you have to install it. It's available as a Docker image. It's available as a binary for Linux. It's available for Windows and Mac. I can speak for myself. If you have a Mac, you can use Homebrew to install TinyGo. Some microcontrollers like the Arduino Nano 33 IoT, what I have here for the examples, will require additional tools to be installed on the machine. But you will find all of these instructions on the Getting Started page. And if you need additional tools, you will find that on the page documenting a specific microcontroller. And in order to build and upload your program, as we have seen before, you just do TinyGo flash, and then you provide the target. The target here in this case, for example, is Arduino Nano 33. And in this code snippet here, I want to build and upload plinky.co. And that is compiling the program. It's writing it onto the microcontroller and also executes the program. So this is all good to get started with it. But how would you debug an application on a microcontroller? And this is some interactive element. I have some ideas on my next slides how to do it, but I don't know, maybe someone from the audience or from the remote audience has an idea how you would do that. Okay, all right, no worries. So you can use logs for it. So in order to debug your application, you can write logs. You can even connect LEDs to your microcontroller. And then depending on the pattern of the LEDs, how often they are flashing, you can communicate error codes. I don't know if you have seen on a Raspberry Pi, you have like different LEDs for like the disk usage, and then the LED, if there's like some error, it's like flashing in different modes. But the most simplest way is writing logs. And these logs are written to the serial console, to the serial output of the microcontroller. And when you connect the microcontroller via USB to your computer, you can read that output. And there are multiple ways how you can achieve that. So if you're on a Mac or Linux, or if you have Windows with Windows subsystem for Linux, then you could use the screen output or the screen command to read the output. Of course, you need to find the right USB adapter first, and you can run the command I have shown here, this ls-al/dev/cu.**, or on a Linux machine, you maybe have to look for TTY. Or you can also use the Arduino IDE to read the output. For everyone who wants to know a little bit more about the serial communication, on this slide, I will provide a link here where you can read up a little bit more. So that's the theory to begin with. And I would say, let's get started with it, and let's do it. As mentioned in the beginning, I want to get started with WebAssembly. So I've prepared 3 examples. One is a simple add method with calculation being done in TinyGo. Then we have the same add method, but the whole setup is done in TinyGo. And then we have a more advanced example with HTML canvas elements and TinyGo interaction. So I want to start off with this code here. And let's take a look at this add.html. So what you see here is a regular HTML page, which does not do anything fancy. It has 2 input elements. It has a button. In these input elements, you can type A, or you have value A and value B. Once you press the button, we call a method called A. And when you press add, or when you press the button, we then read the output of A and B, and then we pass it over to the WebAssembly, which is then being calculated by Go. And in the beginning, we have this script part here. So you first have to load your WebAssembly execution environment, and then we have this add_wasm.js. If we take a look at it, you see that we define a URL of the WASM file, and then depending on the support of the browser, we will load that WebAssembly and hook it up to the runtime environment. So if we now go over to the example output, let me find the right browser window. All right, so if we go over here, you see a web page. Let me just reload that for you to start off fresh. And let's open the inspector here. So if I type in here 4 and 7, and I click add, you see that we have the output of 11 here. And it doesn't look like much, but actually this 11 here is coming from TinyGo. And if we go one more time back to the code output, or to the code in itself, I just showed you the HTML page. But if we take a look at the Go implementation, it is still very simple. We have an empty main function, and then we have a add method. And by using this comment, so the / export and add, we tell the WebAssembly environment that we want to export this add method.
Could you make it a little bit larger?
Sure. One second. Is that enough or is there more?
More, please.
Okay. Let me see if I can find the.
Better? Okay, thank you.
Okay, no worries. All right. So it's just using the export here, and it's no witchcraft here. It's just A and B, and then we return that back, and then we also say print ln here to print out the output. So if we now look at the second example, I have a similar setup of the web page. However, I don't have any JavaScript in here except the WebAssembly execution environment and the go callback _wasm.js. So that is again just loading the WebAssembly file, similar to the one I showed before. But again, here you have A and B, and you have the add button, but there's nothing hooked up to it. And if I go back to the output here, let me also make this bigger. And if I open up a different web page, I can do like 1 + 2. And you see it's still executing this. It's still printing out 3. So from this point of view, it doesn't really look, the output doesn't look different to what we have done with the previous page. But all of the magic is happening in the Go file. And what I have here now is that I have actually some logic in the main function. And we need that to set up our callbacks to still execute our add method. And I mentioned earlier that WebAssembly applications and JavaScript can interact with each other. And that's why we are able to use the JavaScript package and then execute like regular JavaScript like functions, like we can get a document. On the document, we can call getElementById. And by doing that, I can now add a onClick handler to the button. And I can actually say that the onClick handler is a function of this Go function here. So in the JavaScript environment or in the WebAssembly environment, I can hook up this add function, which is on the hooked up to the button. And when I press add, it's doing the same calculation A and B, but we read out the input elements from the HTML page via WebAssembly. And the last example of WebAssembly is what I have called here the more advanced example. And I will hide this one. And I'm using a HTML canvas element here to move this block around the screen to change the color and also be able to say, okay, I want to show traces or I want to increase the speed. So this is all regulated or all handled via the WebAssembly application. And if we go back to the browser, not to the editor, you can see that the index.html page is similar. We set up some CSS styles. We set up the settings box. We have the canvas element, and then we just have some basic JavaScript functions, which in the end just call the WebAssembly code. So there is no render logic in the JavaScript in itself. It's all within the main function here. And again, similar to what we saw before, in the main function, I get the document. And then once we export the start function here, and then basically we start the whole render loop. I will not go through that in detail here, but you can see that we just can call regular JavaScript calls or regular also canvas calls. So I can say now, okay, I want to get a canvas context, a 2D context, and then I can draw with this context object. I can call stroke style or fill style. I can draw lines, and I can do all the drawings. So everything what you saw before is just done with this context.set and so on. And then we have the render frame, which is then rendering one individual frame. And this is all for the WebAssembly examples I have prepared. I would like now to show you the examples for the Arduino a little bit. And I would like to show you some Hello World example. In the microcontroller world, you usually know this as a Blinky. Then I want to connect a LED with a button. I want to show you Go routines, connect a temperature and moisture sensor. And then in the end, I want to connect this temperature and moisture sensor to a RESTful API. All right, let me first show you the microcontroller here. So you can see on this view, you see the microcontroller. So this over here is the Arduino Nano board. The focus is a little bit off on the cables here, but I hope that you can still see the microcontroller here in this corner. I connected some LEDs to it. Over here you see the temperature and moisture sensor, and that's the main setup I have prepared for you. And here we see the first example I prepared for you. So in microcontroller world, the examples are usually what I mentioned. You have a you have a LED which is like toggling on and off. And as you can see in the microcontroller here, that the LED is like constantly turning on and off in a second interval. We can now take this code and we can go over to the Go playground. Yes, and if we plug this in here, let me quickly change the main package. So let's call this main and call this also main. Then you see that the playground will compile the application and run it on the controller. And now you see the exact same thing as you saw on my screen, that a LED is flashing on and off. And also in this playground, you can, for example, add a LED to your sketch, so to say, and then you can hook up this LED to the example microcontroller here, and it's flashing as well. So this is the first example. It is just the Blinky. It's the hello world of the microcontroller world. If we now go over again in the second example, on the microcontroller board over here, we have a button. So, and in the second example, I want to connect this button to my LED. And to do that, I first have a input here. So I say which pin on the board is to which input on the board is the button connected, and to which pin is the LED connected. Since I'm using a global main.go file here, I just call this function run, but it will be similar if you just connect it to or plug it into a main function. So in order to configure your LED, you just say, okay, you have the pin here, and then on this pin, you can just call configure, and you can say what kind of configuration you want to have. So we say we want this LED pin as a output, and the pin from the button, I want that as a input here. And then we just have a endless for loop. So I set the LED to the value of the opposite value of the state from the button, and then I sleep. So what the expected behavior should be is that when I press the button, that I want the LED to turn on. So let me switch the example and upload the program. Okay, I didn't import out. Okay, it has the flash error because it tried to run it without having the proper import. If we do it again, I just have created a make file to shortcut the flash command, but you see that it is actually the same command as I showed you earlier. So if we execute this now, you see that now this LED on the microcontroller was also flashing. And this is because this onboard LED is connected to the microcontroller. And I want to show you, so I want just to highlight you again this example here. So what I said earlier is that we want to toggle the LED when I press the button. So if we now look at this output here, you see I'm not pressing the button, but the LED is turning on and off. But if I now engage the button, the LED stays on. So does anyone in the audience know what's going on? Okay. So we experience here something which is known as a floating pin. So a floating pin is basically, or first of all, for a microcontroller or in a microcontroller world, basically a low pin is a 0 state and a high pin is a 1 state. And a microcontroller only knows if a pin is high if it reaches a certain input voltage. So this microcontroller here works with 3.3 volts. And it, for example, if it reads more than, let's say, 2.5 volts on the input pin from the button, then it says, okay, this button is high now. It is basically engaged. And everything below 1 volt, let's say it's a low reading. But there is like this danger zone in the middle. And with this danger zone in the middle, you basically, if the pin is left open, so basically not connected right now, then it acts as kind of like an antenna, and stray radio frequency can actually bring the pin above the threshold, and this causes a high reading of the pin. And to solve this problem, you can use a pull up or pull down resistor. So how does a pull up or pull down resistor work? So let's assume we have this pull up resistor here. MCU stands for microcontroller unit. The pull up resistor works in a way that if the button is not engaged, if the button is not pressed, we will always read 3.3 volts from the input. And we can do that by using a resistor, which is connected to the input voltage. And then it's connected as a default input to the button. And if the button is pressed, now we create a, not a shortcut, but we create a path for the voltage to travel from 3.3 volts down to ground. And if that is the case, then we have a low reading on the input here, because we now know, okay, if we have 3.3 volts, it's high, but everything else we can consider low. And a similar thing is also for a pull-down resistor. So you can pull down the input of your microcontroller to ground if the button is not pressed. So you will always have a low reading. And once you press the button on the microcontroller, you will always have a reliable high reading. And you can do that from within the microcontroller. So most of the microcontrollers available on the market support a internal pull-up or pull-down resistor. And also TinyGo supports this. So earlier I showed you can configure your pin as machine.pin input. But if you now say pin input pull-up, you can configure a pull-up resistor. So I just want to round up the example. And I want to show you that I have like a 10 kilo ohm resistor hanging here. And I want to simulate like the pull-up resistor, because if you trace this orange cable here, it eventually connects down to the 3.3 volt rail of the breadboard here. So if I now connect this resistor here to the output from the button, you will now see that the floating has stopped. So we can look at it for the next 10 minutes and it will not turn on anymore. But it will turn on when I engage this button. And to just show you, I can remove it again and the LED starts floating again. All right. So as mentioned, you can do that in the code. Here is the same code. If we take this example, upload it to the microcontroller, we basically we're able to do the same thing as we just did with the 10 kilo ohm resistor. And as you see now, if we switch back to the bigger view, the LED stopped floating. So the LED is not doing anything, even though the 10 kilo ohm resistor here is not connected. And now if I just press this button, the LED will turn on. Okay, the next example is I have prepared for you is Go routines. So I have on this board here, we have two LEDs. One is the yellow LED, one is the red LED here. And what I want to do now is I want to use Go routines to turn them on and off in a different interval. So the first one turns on and off within a second interval, and the second one within a 500 millisecond one. And if we change our, and you just do Go routines as you do regularly with normal Go functions. Just say Go func and then the body of your function. So you can, and then since we have two Go routines running, I of course need to somehow make the microcontroller do nothing, so to say. So in this case, I just print out one character and sleep for the next 10 seconds. So let me change this example here. Say we want to run example number 4. And then we flash it. And then once the flash process is done, you will see that both LEDs will flash in different frequencies. So you see that both are having a different frequency. And the nice thing is you can even take the code, what we see here. Oh, sorry, wrong window. Can even take this code, what we see here, go to the playground, if I find it. So we can go to this playground here, can replace everything. We can say, I have package main and function main. Let me quickly check what is the output D4.
You're not sharing the browser right now?
Oh, sorry. Yeah, thanks for telling me. So, yeah, like I said, I just plugged in everything here, what we saw in the Golang before. And let me just connect this LED here to this port. So if we say, want to connect this here to this pin. Oh no, it's actually. So you see that even in the playground, we can have the same Go functions and we have the same output as we saw on the microcontroller here. And again, in my personal point of view, I find that really amazing. Okay, next up is an example where I have a temperature and moisture sensor. So the sensor is this white box over here. Again, first of all, I use the driver for the for the sensor here. So I use the drivers package from TinyGo, and then I just have to configure again my different inputs that I want to have the button input. I want to have the input from the moisture sensor, and also when I read the moisture sensor, I want that the LED turns on. That is my example here. I set up everything. The only difference how I set up the sensor is that I say dht.new instead of like pin.configure. And then this is just basic logic. I have an endless for loop. I read the button state. If the button state has changed from the previous loop, and the button is now true, I read the sensor. And you also see that we have a print command in here. So I want to also to show you that we can read the output. So if I go now over here to example 6, and we compile everything. Takes a little bit longer now because it has a little bit the drivers from the temperature and moisture sensor are a little bit bigger, and that whole optimization package has to run. Yeah, it should be done momentarily. Yeah. All right, and now I have in my make target, I have something called make. I think it's called make screen. No. So I have this make serial here, which is reading the logs from the microcontroller. And if I now press this button here, I actually says could not take measurements from the sensor. Okay, I don't know what happened here. That should work. So that's now the the nice example of when you want to show something that's not working. Let me think. Could not take measurements from the sensor. No measurements done.
We are slowly
Yeah, from the
of time, so maybe we can skip it.
yeah, yeah. From the top of my head, I don't know how to fix it right now. But I did a previous one of this talk before and was basically printing out the output here. Then unfortunately, the other example doesn't work as well, but I just want to highlight that you also have Wi-Fi drivers available. So in this other example I have here, you can use something called Wi-Fi Nina, and you can run the connect to a Wi-Fi hotspot. And then I have configured the same example here, and it's just code to connect to access point. All right, so that's a little bit unfortunate that the last two examples didn't work. But yeah, so here on this slide, you see the two repositories I have prepared where you can find the WebAssembly examples and also the examples for the microcontroller. And then that brings me to the end of my presentation. Thank you very much for listening.
Thank you very much for your talk. There's a question in the chat. Is there a way to know if a third-party package is not compatible with TinyGo?
I don't know of a way. It's usually a trial and error. That's the way you usually go. What I did for the JSON or for the web for the example to push something to a RESTful API, I usually just search what I want to do, like JSON serialization, TinyGo, and then that's working. Then you find something.
Okay. Any questions in the room? Okay.
All right. Thank you.
Thanks again. That was great.